Hi. Before we got started, I wanted to give you the chance to look at something we've done before just to get your mind in the chemistry mindset. So take a couple minutes, pause the video, go to table I, and I want you to try and fill out the information that's there, but just to remind yourself of where we've been. Okay, so I'm going to assume you paused, you wrote it, you unpaused. So I'm going to draw mine on the right here. From table I, we can find the reaction for the combustion of methanol. This is probably, no, looking at it, this is definitely not balanced. I see 4 H's there, so I'm going to put a 2 there. I see 1 carbon, we're good. We've got 4 oxygens there, and we've got 3 over here, which I'm not terribly happy about. I think what I'm going to have to do is I think I have to multiply this by 2, which means that this is going to become a 4, and that'll be a 2, and that should be a 3. Now, you knew all of this, hopefully, because you were able to go into table I and find this reaction, and this reaction should already be balanced for you. But it's always good to, go through the practice of balancing a chemical reaction just to make sure you know how to do it. But the really important part from what we learned from table I is that the delta H for this reaction is less than 0. So that should inform us as to whether or not it's exo or endothermic. And that's actually going to need to come into play when we're drawing our reaction. So on our y-axis, we've got potential energy, or H, and here we've got the reaction proceeding from left to right. So we're going to call this reaction exothermic because the delta H being less than 0. And in terms of drawing this, that should mean that the energy of the products is lower than the energy of the reactants, so that our reaction coordinate looks something like this. We need to label the delta H value. So I'm going to switch my colors really quickly. The delta H value should be the space from beginning to end. So it's this height here. The energy of the products should be this height here, from 0 to the products. From 0 to the reactants over here is the heat of the reactants, the energy of the reactants, and then the amount of energy it takes to get from your starting point up to the highest point is going to be your activation energy here. So I think I've covered everything. We've got delta H, activation energy, products and reactants. We already said it was exothermic, and that the energy of the products to the reactants. You can see here that this height here for the products is less than the reactants, so that the HP is less than HR, so that HP minus HR is less than 0. I want to take things in a completely different direction today now that we've got that out of the way. I just want you to think of 2 decks of cards. I wish I had them here. I left them at school, unfortunately. But if you can picture one that's shuffled, been used already several times, and one that's new, if you wanted to go through the process of shuffling both of them, which you think would happen with more probability? Would the shuffled deck, once shuffling, suddenly be in deck order? Or would the new deck become what we would consider shuffled more quickly? Now, I hope most of you agree with me on this one, that taking a deck that is new and shuffling it until it is shuffled is a lot quicker, would happen with more probability than to take a deck and shuffle it until it's shuffled. I'm sure there's some statistics out there as to how likely it is for that to happen. I don't have the numbers off the top of my head, but I'm also trying to avoid some numbers today. So our big question today is why? Why is it that when you shuffle a shuffled deck, it is less likely to make an ordered deck? And this simple example actually displays something, and I'm going to do this very poorly, so people on the internet are probably going to call me quite wrong, but just go with me for a few minutes. The idea of something called entropy, not enthalpy. Big issue, lots of E words this unit. But we're going to define entropy in this course as a measure of the disorder or the freedom or the randomness of a system. So in terms of how entropy works in the universe, the law of disorder, which stems from the second law of thermodynamics, is that the natural tendency is for systems to move in higher disorder over time. So this here being our second law. Order. Well, order's got a bunch of definitions. We're going to take a look on the next slides. But for us, order is going to be thought of as molecular organization. This is a massive oversimplification, I know, but we're trying to start with simple and then we can build up some bigger ideas soon. You might remember the second law of thermodynamics that I'd mentioned before. I'd said that the second law was that heat moves from hot to cold. And that is still commensurate with this statement here. The most disordered, the most free system is one where the energy is as evenly spread out as possible. If you want to think of it in terms of the deck of cards, the most disorder would be to have the hearts as evenly distributed over the deck of cards as possible. It's more probable when shuffling to have the hearts evenly distributed throughout your deck than it is to have all of them at the beginning or all of them at the end. Yeah, is it possible to get some hearts closer together than others? Sure, but that's talking about one situation, and we're trying to think about all situations. So what I want to take a look at is actually, like we were talking about with enthalpy, I'm less concerned with the entropy of a system on its own. I really want to focus more on the change of entropy as a process happened. So the letter for entropy, the variable, is actually the letter S. Don't ask why, because randomness. Now, there is a reason. I don't know what it is. But we're going to worry about the delta S for a process, which, like H, would be equal to S for the products minus S for the reactants. In this case, if the products have more entropy than the reactants, then this value is going to be greater than the value of delta S is going to be positive or greater than 0. So how do we talk about making a system more or less organized in terms of molecular arrangement? Well, we're going to take a look at that on the next few slides. So first, one of the first ways I want to look at is talking about phase. So if we had a block of ice, that would be here, the solid phase. This would be like if you took the sample and melted it, and then if you took that liquid sample and boiled it. I would say that as the image shows, that the entropy is increasing. So we could say as water as ice becomes water as liquid, delta S is greater than 0, or this is an increase in entropy. If you were to look at the particles, I mean, if we go by our definition of just order or disorder or organization or randomness, it does appear to me that the particles are less ordered in a liquid sample than they are in a solid sample. There's more rules as to how a solid is formed, and so statistically, it is less likely for a group of particles to spontaneously be a solid than they are to be a liquid, or there's more ways to make them look like a liquid. There's a number of ways to think about it, but the way I'm looking at it, if we just think about in terms of organization, liquids are less organized than solids, and gases are less organized than liquids. If we took the same solid block of ice and we hit it with a hammer, you could also look at one big sample, like one crystal, versus several tiny grains. And in this case, even though it's a physical change, we would consider this an increase in entropy. Similar to the previous example, if we were to take a sample of just one phase, like water, and say that this is at room temperature, say, this would be like 20 degrees Celsius, and maybe this is 50 degrees Celsius, and maybe this is 90 degrees Celsius, we can see that like the particles themselves look less organized in the 90-degree sample. Even though a liquid has more entropy than a solid, and that's a positive change in entropy, even within a liquid, hot liquid has more entropy than cold liquid. Because, as you can see, the particles are less organized because of their speed. In fact, if we wanted to get into a few tiny numbers, the units for entropy are actually measured in joules per Kelvin. So there's this idea of if the Kelvin increases, the joules have to increase too to maintain that proportion. And the joules being this energy, that's how we're measuring our entropy. Finally, I wanted to take a look at some chemical reactions because yes, there are physical processes to look at, but I think chemical reactions are really where we start to see a lot of applicability of this entropy idea. So for the decomposition of water shown, two waters becoming two hydrogens and one oxygen. There's a couple reasons why I would make this comparison and look at it as an increase in entropy. First off, we've got two particles here, and then we actually have a sum of three particles over here. These three particles are less organized than these two. Additionally, we've got two different kinds of matter in our products and only one kind of matter. Every particle here is water, where these we've got particles of hydrogen and of oxygen. So we're going to see in these cases, for delta S to be greater than 0, products should be showing, we should be showing more moles of products, we should be showing more compounds, and we should be showing more gas or liquid. So in this case, we've got gases for all three particles, so that's not really helpful in terms of an entropy calculation, but the fact that we're going from two particles of one substance to three particles of two substances means that the delta S in this case should be pretty positive. Just to quickly sum things up, I wanted to give you three examples here to look at. I want you to take a minute and think. I'm actually going to count to like 15 here, give you about 5 seconds per, if you're not going to pause, so that you can try and determine whether the entropy is increasing or decreasing in each case. So in looking at our first example, using our three metrics, we've got phases, but again, all three phases are the same. But here we've got 4 particles of two substances becoming 2 particles of one substance. So I would say that the entropy here is decreasing. For the second example, it's both the same substance, but the transitions from a liquid to a gas. And so here the delta S is going to be greater than 0. And then for the bottom one, we're going from one solid to one solid plus one gas. So because we've got more particles and more gases, it's going to be positive. As a final thought, we could also separately talk about the enthalpy of each of these, separate from the entropy. There's no tie between them. But in this case, you'd have to go check on your reference table for I, but I'm pretty sure that the delta H here for the formation of ammonia is negative. I'm not 100% sure on that. I might need to correct myself. Putting a note here for myself to check that after this. This one, obviously, the delta H is going to be positive because we're talking about a vaporization step. And here, this is a decomposition. So again, I'm going to assume that it's positive. I'm going to check on these two just to be sure, though. One final thought to leave you with. I'd mentioned this law of entropy at the beginning of this. There is a law here. In nature, there's a tendency of systems to favor certain changes in enthalpy and entropy. And it's really, really easy to draw the analog to systems that you see in your life. But let me just write it first. In general, systems will favor lower enthalpies and higher entropies. The classic example I always give is when you think about the state of your room and how organized it is. Yes, some of you might have cleaner or dirtier rooms than each other, but in general, if you do not spend energy on cleaning your room, the room won't stay clean. When nature takes over and no humans are interacting with it, the system of your bedroom or your living room will tend towards lower energy because no one is expending energy on it, and a higher level of disorder, to put it nicely. If you have any questions about this, you can post below a comment as a question or email me, but hope this helped. Thanks for watching.